Good morning, everybody. Welcome to the Friday Informatics PowerTalks series. I'm very happy to introduce today's speaker, Dr. Dongxiao. He's professor of computer science and the founding director of the Wayne AI Research Initiative at Wayne State University. He earned his Ph.D. in bioinformatics from the University of Michigan, and his current focus is on trustworthy AI application to social health and urban computing. He has over 100 peer-reviewed publications and has served on review committees for flagship AI and machine learning conferences and premier biomedical informatics journals. He has multiple NIH, NSF, and private grant funding projects. The title of his talk, Enhancing Algorithmic Fairness in Deep Learning, Discovering and Mitigating Spurious Features. Dr. Zhu.
Yeah, thank you for that nice introduction, Amy. Yeah, today I'm very happy to report our most recent work on the algorithm fairness with some potential applications in the healthcare domains. So our approach is to, so when you heard about algorithm fairness, so the multiple approaches to leading to the fairness. So our approach is to discover and mitigate spurious correlation. It's kind of relatively different approach. Yeah, so first I'd like to start with the very exciting paradigm shift from AI, from traditional discriminative AI to the generative AI. So right now is on the left panel, you can see the, sorry. Yeah, on left panel, you can see what was happening yesterday. So people are building the classifier using the real data and for each specific task, and those models usually do not generalize well to the different tasks. And there's also people do the post hoc evaluations. For example, this is the standard use case, right? Try to do the targeted target detection in the image, or you can think about, we can also label the different organs in the medical images. So for these days, it's transformed to the foundation model-based approach. I wouldn't say all of them, but it's become more and more. So instead of using the de novo trained models, we use pre-trained model. Instead, we directly get into the inference stage. We prompt the pre-trained models, typically using natural language. And so the model is generating model. It's not just to try to tell A from B, but it's generating new content, and with the new emergent abilities. So the model with the few shots can be quickly adapt to the new task, and also the model hopefully align with the human and the human values. Right? So that's the what's happening right now. Yeah, there's some foundation models. Some are generating the images like Dolly and Stability AI, and also some generate the language, and also some generate the computer code. So, but one thing shared in common will be the prompt or text prompt using the human natural language. Yeah, that's one example for the text prompting. So you can take any prompt, we can generate the language content and the image content. So those are very powerful features leading to new scientific discovery. But however, I'd like to here I'm try to give some caveats of using this new tools, right? So we're talking about the risks, right? Risks pair with the opportunities. So the one of the more major risk I'm trying to focus on is the social bias. So for example, so you can see that when you use the text language generator, right, text generator, right. So it's often the case you can see the generative language, right. So you have the one example is social bias. You can see the gender associated with the profession, right. So you can see the gender she or female is often associated with the kindergarten teachers, and then the gender male often associated with the construction workers or mechanic workers, things like that. And a similar situation also happens for the, for the text to image generation. So on the left is text to text. On the right is for text to image generation. You can see the, if you see the, basically the language, the image generator going to use the keyword like nurse to generate the image, right? So that's what we call is the spurious correlation. So so in this case, you can clearly see the definition. So in the generation content, so the profession is, for example, you like to generate the profession or you like to generate the gender, then the spurious correlation will be the, it's the it's a gender profession correlation between the gender and the profession, and also the image and the profession, or image and gender. So yeah, so then another risk will be the safety. So that's also we are working on. So for example, jailbreaking. So on the left, there's still language generating. So you can basically, you can tweak the prompt, right, to elicit the language model to generate the we call adversarial prompt. So you can put some adversarial token here to trigger the so-called jailbreak event. So the language model will output the content. It do not align with human values. So same thing for the stable diffusion as well. So you can also, in this case, you can also see by putting some adversarial tokens, the output image also change a lot. So that's bring a very serious issue, right? How stable of this system are. So there's many ways to address it. So our way is to see what feature they have leveraged to do the generation and to the discrimination. So we call it spurious feature. Yeah. So in summary, the challenge we have here will be aggravated ethics and safety risks, right? So from the current yesterday model to next generation models, foundation model based. So so our research question, we target 3 interconnected research questions. The first is why we care about fairness, algorithm fairness, right? So based on that, the quick answer to this question will be we try to ensure the equity, right? Equity for all, right? Equity for all the outcomes across the social groups. So then the follow-up question will be how to discover the social bias, right? So for example, how to discover what is the sensitive attribute. So when you see the bias, you always link it to the attribute. According to what attribute? For example, according to the gender, it is biased. According to the race, or according to any other attributes, it is biased. So how to discover it? The third is how to mitigate it. So that's a 3-step research question. So first, why algorithm fairness is important. Of course, that's the align with our social values, right? And it's equity for all, right? So no matter what area, what science domain we come from, like health, humanity, and law, and finance, we all hope to have the equal outcomes across the groups, particularly for the underrepresented groups, right? So so here our approach from algorithm side, we try to first detect and mitigate the bias in the training data, and then our approach here is to detect the bias by explaining the models to find a spurious correlation. So the key here is explaining. So assuming you have the pre-trained, right, language model or vision language model, you try to first explain the outcome, right, to see what features has leading to the bias outcome. So we use explanation approach. So once we find the spurious feature, then we try to fix it. So the approach we use is try to design adversarial attack to fix this spurious feature. So so that's the kind of overview about the 3 components. So our goal here is algorithm fairness. So we ensure our algorithm to have equal outcomes as defined by the attributes of interest. For example, gender and race. And then our approach here is to find the spurious features, and also we try to fix it. So that's the kind of outline of our approach. Yeah, so the major dilemma is how to find what is real features and what are spurious features. As you know, the ideal case for any predictive model we use, right? We hope to learn the real features. We don't want to learn spurious feature, right? Because the real feature is gonna be genuinely correlated with the target. So I'm gonna give some example in next slide. What are real features? What are spurious features? So once you have the real features, so it's gonna generalize well and also equitable for all. So that's the key. As long as we can learn the real features, so we can hope for the good outcome, right? The equitable outcome and fairness across groups. But unfortunately, in reality, so the features we learn are not real. So we call it spurious features. So that means sometimes in other literature, we also call the shortcut features. So those features are spuriously correlated with the target. So unfortunately, in many cases, our prediction model learned this type of features and use those features to make the prediction. So those type of models are biased. It does not generalize and prompt bias. So that's the dilemma. So some examples about what the spurious, what are real features here. So the top row here represent the spurious features across different use cases. So the second row corresponds to the real features. So let's start from the simplest case, right? So if we like to build a model to tell, the shape, right? So we have circle, we have square, right? So the real feature will be the reddish shape, right? So the way to tell this is circle because the shape, not because of color. So the spurious feature you can see because the small training set, right? They happen to be the case that all the circle are red. So all the square are green, which is a fake because in the real world, right? So certainly not all the circles are red. Some circles are green, some other colors, right? So that's leading to the model to learn the spurious feature, which is the color. So basically, the model mistakenly couple the color with the shape. So that means when the model see the color red, you're gonna see this is a circle. When the model gonna see the color green, the model gonna see square. So that's the spurious correlation between the color and shape. So the correct way to do it is to actually decouple the correlation between the color and shape. So that means one way to do it is just to make the synthetic data set, right? So that you can see the circles can be any other colors, right? So the square likewise can be any other colors. So they call it the mix up, right? The data mix up. So to try to decouple the spurious correlation between the shape and the color. So with that, then the model can learn the red features. The second is more relevant to the medical imaging case, right? So you can see if the target is to tell the COVID is severe, non-severe, or yes or no, or other lung disease, right? So in the top row, you can see the features, which is in the heat map, highlighting the heat map here. The off the lung, right? Lung is right here, right? It's off the lung. So they are spurious features. So very likely, so those features are corresponding to some kind of ID or batch ID, coming from X-ray machine or CT machine. So this is a spurious feature. After we use explanation approach, right? To find the feature, they are off the line here. We know they are spurious features. So if the machine learning model use this spurious feature, it's gonna make the wrong prediction, biased prediction, of course, right? So what are real features? So real features ideally should be falling into the where the lung is, right? So that's another example about real features. So there are other examples. For example, if you try to predict the hair makeup for the woman, instead of using all the facial features highlighted here, we really need to look at the, just the, lip color and the eyebrow here. So that's what we call makeup. So, and also the dark, right? So the spurious feature will correspond to the anything surrounding the dark, not the dark, right? The real feature will be the dark. So those are some examples. The techniques we have used here is explanation techniques. So we can try to find, what part of the features the model has been used to tell this is the dark or not, to tell this is the COVID or not, to this lung disease or not. Yeah, so for the language part, so this is so far we talk about the spurious features in the image, right? Medical imaging and also natural images. We also look at the spurious correlation in the language models, right? So for example, there's some simple examples that Spielberg is the name of the famous movie director, right? So it's always associated with the positive cases, a positive sentiment. The New York subway is always coupled with the negative sentiment. So these are both Spielberg and the New York subway, they are spurious features. So because not all the cases that Spielberg are positive, right? Not all the cases that the New York subway are the negative. So the right way, the real feature should not be the name of the director, right? Should be other words like the great spinner, right? For example. So the real feature in the New York subway case should be without being stuck in traffic, right? Some other faster, right? So those are actually positive cases. But because the New York subway always linked to the negative outcomes, so that's where the spurious feature lead to the bias negative. But actually, this sentiment is positive. So there's other examples in the language models. You can see the GPT model, right? You can see the local bias, global bias. So basically, the gender has been linked, to the professions you saw before, right? So when the GPT model say the man, they're gonna link to the doctor. When they say the woman, link to the nurse. So things like that. Yeah. So in the next 20 minutes, I'm gonna talk about our technical approach. So I already hopefully I convinced you that the one of the core issue that caused the algorithm bias is the spurious features. So we need to first make sure the machine learning model learn the spurious features. Then we need to find an approach to mitigate the spurious feature to ensure the machine learning model is fair. Okay, so our workflow is start from the inference. So as you know, in this day, the large language model, right, and also the vision language model, they are pre-trained already. So the step 1, step 0 will be you interact with the model by prompting, right? So it's not like a traditional machine learning approach. You train the model. You don't need to train the model. The model has been trained already, right? So you first interact with the model, try to find the spurious correlation. This need human in the loop, human AI collaboration here. We need to find a spurious correlation. Then after we find it, so the next is we have 2 ways to fix it. Okay, so one way is to we do the data augmentation. So we try to use additional synthetic data to decouple the correlation between the synthetic between the spurious feature and the outcome. So example you saw before, right? We try to introduce additional circles with other colors, additional squares with other colors to decouple the correlation, the spurious correlation. That's one approach. Another approach is to attack it. We try to design the adversarial attack to attack it. Yeah, so that's the first approach is we try to find it with the explanation. So yeah, this is refer to the image classification cases where we try to use explanation to find what features that the model has been used to classify the different target, like scorpion, right? So the explanation approach we use is called attribution-based. So you can see that's the features that model has been used. So that's the real features, right? So in other cases, we can also use the predefined concept. define what are real features. So the reason why we do that, because the explanation approach is very unstable. So we try to ensure first our explanation is correct and stable before we try to find the spurious features. So the reason we see it's not stable because we have a adversarial effect and a gradient saturation. So here you can see for example, the vertical axes are the target output, right? Prediction is a cat or a dog or something like that, right? So horizontal axis will be the input, the features, right? So you can see the output surface is very, very unstable here. So you can see sometimes you have this kind of adversarial effect. So that means even you change the input slightly, so you're gonna cause the prediction change a lot. So that's called adversarial effect. So this gonna challenge a traditional explanation-based approach. So that means if you use one image, right, for explanation, if you change it slightly, it's gonna give you very different. It's give you very different explanation. So another effect is gradient saturation. So that means if your input is in this range here, right? So no matter how much perturbation you have the input, right, your explanation will not change. So based on this tool, so we use the solutions instead of using the gradient at any certain point. So when you take the derivative, right, to look at a certain point. So instead of using the certain point, we do the integration of the gradients. So that means we look at certain regions to stabilize the explanation. Yeah, this one formula basically just try to use a range instead of the single point, right? So we try to accumulate the gradients of image interpolated between the 2 points, so that even small perturbation on the input does not change the explanation, does not change the explanation too much. Yeah, so this is the more like a technical details, the how to find the reference, so that we can do the explanation, right? So of course the naive approach here is to use black or white as the reference, but actually this is not justified. So what we use here is we used our adversarial examples and also debiased examples. So in a nutshell, what we're doing here is we try to perturb the image, try to make it being misclassified as another label. We call it other adversarial examples. We use that as the reference. Or we do something on the image, right? We try to remove the spurious features. We also use that as the adversarial, as the references. So two different approaches. Yeah, so here you can see you can clearly see what are real features, right? So if we try to tell this is the cola, right? So the real feature will be right here with the torso here. But the spurious feature will be the tree trunk, right? So it's because the reason we have the spurious feature, because the tree trunk is always associated with the collar. Oftentimes you see the collar on the tree, but sometimes it doesn't. So this is the spurious feature we saw. So it's our early work on adversarial gradient integration, published a few years ago. So we try to achieve the stable explanation of a model's prediction, and we also try to ensure this is feasible. Yeah, so here's some detail I'll skip. So we basically we do the qualitative evaluations. We make sure our approach give the most accurate explanation. So for example, if the target is the elephant, so here we have 3 competing approaches. So first is our approach HAI, and then we have IG, and we have citizen map. So our approach, you can see the features, right? So you can see just like the elephant, right? So that's the real features. So other approaches, you can see the many spurious features all over the place, right? Some are real, but the real feature should be on the torso of the elephant, just like this. But other approach, you can see they learn the feature everywhere. So some are spurious. So likewise for other examples like the lizard or the tree frog. So this is just the qualitative, right, evaluation. We also have the qualitative evaluations. So how, by eyeballing, we know our approach can find the real features, right? But how do you prove it, right? So we did some quantitative evaluations. So use insertion deletion scores. So in a nutshell, what we do here is we try to, for each image, we try to find what are most important pixels. So basically, we take top 5% most important pixels, right? For example, in the deletion score here, we try to delete 5% most important pixels horizontally, 5%. So here, actually 1%. So you can see the prediction performance drop to 0. So that means the prediction label is completely based on this 1% of pixels, which is real features. So for the insertion score, we have also insertion score here. So insertion score means we start from the 0, which adding the pixels, right? So you can see it's only like 2% of pixels, the most important pixels we call features or real features. Adding only 2% of real features can accurately predict this goldfish. So that means this quantitative evaluation basically saying that we learned the most important real feature, only 2%, 1%, that can be used to generalize the model to the different task. So there's also other evaluations using the different architectures. Yeah, so we also expanded the approach to language domains. So we basically we try to find out what are the best explanation methods for the transformer-based model, right? So we try to dissect the information flow in the transformer using the gradient and the self-attention by combining both. Yeah, so this is another work we recently published in Neurips. So here the idea here is to kind of dissect the information flow, right? So once you fit in a sentence into the bird, for example, the bio bird, right? So you would like to see how the information flow through the neural networks to get output. So there's 3 pieces of information. One is attention weights. Second is gradient. Third is the relevant proportions. So the idea here is we try to combine those informations, try to explain the output here. So yeah, so the novel observation here is to dissecting the information flow into the the attention and the token itself. So this way you can we can try to find out what is the most important tokens as input to leading to the output. That's a real feature in the language domain. Yeah, so that's some details here. I'll skip that. Yeah, we also do the evaluation on these different data sets, natural language processing data set. So here you compare with different methods here. So the last segment is our methods. So our method is among the best across all the tasks. We also evaluate in the case that some of the text has been corrupted. So horizontally will be the rate of corruption. Vertically will be the the quality of explanation. So we can see the up to the 50% of corruption rate. So our method, it's actually performed the best compared with other methods. So like this case, if in the clinical domains, you can translate it into for example, to find what are most tokens leading to has been leveraged by BioBERT for the prediction. So it's kind of interpretation approach. So if the token is not quite associated with the target, it can be considered as spurious correlation. Yeah, the second approach is to do how to remove this, how to mitigate this. So we have 2 approaches. One is the data augmentation, another is adversarial attack. So data augmentation I already mentioned. So we try to decouple the spurious correlation, in this case, between the color and the shape. So that means not all the circles are red, and not all the squares are green. So we try to decouple. have the generative model to generate the additional synthetic circles with different colors and the synthetic square with different colors. Yeah, so this is the publishing EGKI. So yeah, this is some technical detail. The idea here is if the spurious correlation is learned by the model due to the limited training set, so our strategy is to augment the training set, try to use the synthetic data to decouple the spurious correlation between the the target and the spurious features. So that's the synthetic data set being introduced. So that's the more like takeaway message. What the strategy we used here. So another another way is instead of making additional synthetic data set, if we have tons of real data already, we don't need to add additional synthetic data. So we can also try to mitigate the spurious features using adversarial attacks. So here's the case. For example, this is the goal here is the target is the hair color and input is the image here. So by using explanation techniques, right, we can find the features, right? So we know what are real features, what are spurious features. So the real features you can see, of course, is on the hair, right? Because the target is the hair, not other part of the face. But unfortunately, many vision transformer or other kind of model, computer vision model, they learn the features are not on the hair, but in the eye or lip. So these are actually implicitly correlated with other target, not the hair, maybe the gender or makeup. So here, the idea here is we first use our explanation approach to find those features. Then we attack those features, put some small pixel here to perturb the feature here to minimize it. So this is the nutshell approach. So yeah, this is a relatively newer paper we published. Actually, the ECCV coming up actually next week in the conference going to be next week. So the idea here is we call it debiased self-attention. So the first, as a kind of recap, is to try to find what are spurious features, right? So what do we do here? We design the bias-only vision transformer approach, right? We try to to learn what are spurious features associated with the sensitive attribute, for example, the gender or race. But this feature is associated with the sensitive attribute, not with the true outcome. So we call this the bias-only model. Okay, so here, so that's happened on the left, right? So this bias-only model, we try to learn the spurious feature, for example, the eye and the lip, right? So then we do the adversarial attack, kind of perturb those features slightly, right? Then combined with original data, we can do the second, we call it debiased self-attention. So this way, hopefully, we can build a unbiased model because the spurious feature has been attacked, mitigated. Okay, so that's the kind of high summary about this paper. Yeah, so in terms of the fairness approach, there's many different metrics we use, not only in the image computer vision, also natural language, medical, informatics, also like this. So we typically use the accuracy, that's for sure, right? We also use the demographic parities. So basically measure for example, what's the difference between in terms of accuracy across the different demographic groups. So if if the parity, if the accuracy is equal or not, that's the one of fairness metric. So another will be the difference of the balanced accuracy. So it's also the very similar roles to compare whether the outcome performance is equal across the different subgroups defined by the sensitive attribute like gender or race. We also have the balanced or equalized odds. So those are different metrics. So we compare with, you can see that we compare with in terms of 5 different metrics. In addition to the accuracy, we have 4 other fairness metrics. So our method is in red solid line here. You can see our approach outperform a wider range of the competing approaches here in terms of all the 5 different metrics. So that's the method comparison showing that our method is able to ensure the fairness by first finding the spurious correlation, then mitigate the correlations. Yeah, so finally is come to the key takeaway of my talk. So I know we cover a lot of different moving parts. So I try to summarize by providing the key takeaways. So our approach here start from the finding the spurious patterns or correlations. So the techniques we use is the explaining techniques, right, in the inference stage. So you can recall the many examples I have already covered. So for example, we can in the medical image classification, you can find some spurious features, right, at the edge of the medical image, not in the organ, right? It falls on the organ part, right? So those are spurious patterns. And also for the facial image, you can see the spurious pattern sometimes have nothing to do with the target. Right? If the target is hair color, then the spurious pattern falls on the other part of the face, not on the hair. So that's also spurious patterns. So once we find the spurious pattern, right? So we try to fix it. So we have 2 different ways to fix it to ensure the algorithm fairness. So first way here is through the data augmentation. So this can be very effective in some domain, but not quite in the healthcare domain because you have to really generate the synthetic data to augment the training set. So it can be risky. But the good thing here is, once you know what are the sensitive attributes, right? So you can always try to generate additional data set to decouple the correlation between the spurious features and outcome. So that's one strategy, right? Another strategy will be we find the spurious feature and we mitigate it by attack. So this both approaches we can utilize both in the retraining or fine-tuning. So in the traditional machine learning area, so you have a smaller model, you can do the retraining. So in the foundation model area, so you can use the fine-tuning, because you have billions of parameters. You cannot do the retraining, but you can do the fine-tuning. So this is how this the 3 parts connected. So the right panel shows how they work together. So the goal here is to achieve algorithm fairness. So the technology we use is to use the explanation techniques to find the spurious patterns. Then we try to fix spurious pattern by using the robustness techniques. Yeah, so that's about it. So so this research and in whole or in part has been supported by some other set of ASF NIH grants and also some local grants. So I'm like to take any questions. Thank you very much.
Can I ask questions to begin with? Yeah.
Also, feel free to put your questions in the chat or in the meeting question window. Yeah. Or you can also speak up and raise your hand.
Yeah. So, yeah, thank you very much. This is very insightful, and we don't normally just hear talks about deep methodology like this, and so I really appreciate it. One question I have is about the refining fixes that you mentioned. So normally we take a very naive approach. We say, okay, the foundation model doesn't train on, let's say, genomic data sets or clinical data sets. And then we just use our own proprietary data sets to train it. And you have figured out an approach that's more targeted, finding out where it's weak and then train it. But what's the difference between the uninformed refinement, hoping for the best, and your targeted, if our data set is the same? Should we just use your approach only for the evaluation part? Or do you think that the fixing part would have also huge impact in our domain, since our data is quite, it's all there? And
yeah. So it depends on whether you want to train your model in-house or you want to use a foundation model, right? So yeah, I mean, if you want to use foundation model, so usually right now is model vendors are tech company. So I know some academia, in the academia also some like genomics and there's some foundation model. Genomics foundation model has also been trained, in-house. So in that case, no matter this is provided by the tech company or you're training in-house, so the step one is always to find to do the inference, right? To find the cases and the query the model, prompt the model to generate outcome. So the explanation techniques comes here, right? So you try to through the inference. So you try to find out what are the most important feature that the model leverage to give the response. So so if the goal is debasing, you can intentionally use some the sensitive attributes, right? Try to kind of see what are spurious features has been leveraged. Then through the fine-tuning process, so those spurious features can be mitigated. So that's for the foundation model part. If it still do the traditional machine learning, with smaller data set, so the most straightforward way will be the retraining, and you can do some data augmentation, provide some additional synthetic data to decouple the correlation between the sensitive attribute and outcome. So does this answer the question, or you want to rephrase?
maybe not completely. So I was just saying that the fixing part is very tricky because in biology, collecting data is very expensive. And if we want to try to fix it, if your suggestion is to generate a synthetic data, yes, we can. But usually the biologists generate experimental data, and that experimental data may still have bias. So you may have pointed out the algorithm bias, but I was suspecting that the inherent bias of data and the algorithm is intertwined. We don't know. Actually, we are very much convinced that the data was trained in a spot and biased in many, many ways. And for example, if you there may be a lot of data, but if you study a very rare disorder like ALS, there may not be enough data. You only have enough data to refine the model. And then, so whether to use your approach or not may not have a huge impact on how we do the biology. That's a complication I was trying to point out. And also even for the detection part, we sometimes don't know what is a spurious feature. Like in your COVID example, yes, it should be in the lung, but sometime early COVID, it may be on the upper tract, and it just take a day or two before it gets into the lung. and the science is not that clear. A lot of the epidemiology study also cannot make conclusions whether vitamin D is, for example, is for sure helping or not helping with certain disease conditions. So we don't know what is spurious and what is not. How do we deal with a situation like?
Yeah, that's a very insightful question. So regarding this for the spurious feature, many features are latent. You don't even know what they are and what type of feature they are. So it's important to define what are the sensitive attributes. Because for example, in the fairness domain, right? When you talk about the fairness, you talk about the fairness in terms of what. So of course, frequently used the sensitive attributes will be for example, gender, race, right? This is the frequently used. But there are other latent, latent variables that can also be treated as the spurious feature. Sorry, so can we use the sensitive attributes to define the spurious feature? So the challenge here is not in the knowing, because we are dealing with the knowing, and which is the easy case, right? You know what is spurious, what is the sensitive attribute. Then the more challenging is knowing unknown, right? So you know what is the sensitive attributes, but you don't know what the spurious features. But the most challenging part is I know, right? So you don't know what is sensitive attributes. You don't know what is the spurious feature. You know nothing. So that's more like an open-ended question. Challenge. So what we've been doing so far is really deal with knowing known and know unknown.
Well, thanks for the great talk. I have some quick questions. Following on what Jake said, how are the spurious features being detected? So is this after the fact where you look at the results and you say, oh, it looks like it thinks that all squares are green or whatever? Are you seeing it after the fact and then you're going back and saying, oh, well, so we need to tweak that model to fix that? Or how are these things? That's how these things are being detected?
Yeah,
And
yeah.
how do you, no, go ahead, sorry.
Oh, you go ahead. So I just try and agree with you. I think that's the major approach to detect a spurious feature is really empirical human AI collaboration. So domain expert. So we provide explanation techniques. The domain expert are gonna look at the explanation, right? Gonna look at the features has been identified by our interpretation approach to see if it makes sense or not. Right? If not make sense, then it's very likely to be a spurious features. Then they come back to us to refine the model, do the retraining or fine tuning, try to encourage the model to move closer to the real features.
Okay, and then kind of also following on that, how do you overcome this bias when there's so much of it, it's so pervasive, such as like say the example of the construction worker, since probably most construction workers are male, but you want to have the system not think that construction workers are by definition male, then you have to flood it with a lot of your synthetic data or your interaction before it will overcome that huge bias. So that's my first question. And then also when you're adding so much to this synthetic data or these, you're giving the guidance, isn't there a risk that you'll overcorrect and cause unintended consequences?
Yeah, that's very insightful, very good question. Yeah, so the synthetic data augmentation is one approach, right? So I think what I mentioned here is in the traditional machine learning domain, you don't have a lot of training data. So that's the reason you see the fake spurious correlation between the profession and the gender, right? Because the data is limited, or because it's from human bias. Accumulated in the past year, decades, right? So you don't have a lot of data. So that's the only approach is you supplement with the synthetic data, try to decouple the spurious correlation. For in the foundation model part, so you have tons of data, then in the fine-tuning stage, we can kind of, from model level, encourage the, to ensure or penalize the, the generation based on the sensitive attributes. So there's the multi level, right? Pre-training, we can augment with the synthetic data. Algorithm level, we can penalize the generation of the, the spurious correlation. We can discourage from generating. So from different levels.
Question from Kevin Song. Could you create an automated reinforcement learning from human feedback RLHF system to detect spurious features and correct for bias?
Oh, human feedback. Yeah, that's very good. I think you are definitely working this area. Yeah, so that's actually in the foundation model, in the generative model. So one important area is the alignment, right? So how to make the ChatGPT or language model or vision language model to align with human value and the social norm. So one of the more important approach, if we talk about alignment, it must be a reinforcement learning. Right, so that means the human feedback gonna give a word, right? Try to encourage the generation process to be more aligned with what the human need, a social norm, right? So, but here we're not talking about alignment yet. We're talking about fairness. So, so it's more likely, there's a very simple social norm there, which is equity. It's not like in the open world generation. So for example, you don't want the ChatGPT to generate a harmful language or toxic language or an illegal or dangerous risk or an unethical statement. So this open world. So that's, I think, a reinforcement learning is very useful. But for fairness domain, it's just simple, equity or not. Yeah, but I think it's very, very insightful questions.
Other comments or questions? Oh.
Yeah, you are right. Yeah, then I think that Kevin has a follow-up question. Social norm can also change the definition of bias over the time. Yeah, you're absolutely right. So we are talking about when you see the bias, right? You always, the first question, you bias against the what? So that's the sensitive attributes we are talking about. So right now, for current social norm, right, the sensitive attributes mean gender or race, right, or ethnic background or cultural background. So those are current social norm. You're absolutely right. But after 20 years later or 30 years later, then social norm change. Then the sensitive attributes also change. Right, but no matter what are the sensitive attributes, so in the fairness domain, it's always to ensure the equal outcome across the groups defined by the sensitive attribute. So does it make sense? Oh, thank you.
Other comments or questions? What kind of what's on the horizon? What can we see coming with this work? And what are some of the maybe some of the challenges you're addressing?
Yes, so the fairness is just kind of inherited from the history. Right now, I think the Kelvin Song already pointed out the more kind of serious issue on the rise will be the alignment issue. So responsible use of AI, right? How to ensure the AI, generative AI, how to ensure the generative content align with human value and social norm. So that's the most critical challenge of a society.
Yeah, I also like to comment that this is something that we need to think about and a lot in medical applications. And there's one example, you can say when we talk about breast cancer, we like to think, oh, breast cancer is for female, but actually there's a male breast cancer. And if we don't just collect data and address that, then those maybe 2% of the patient will suffer. But even if we know about the fairness issue, the generated by AI foundation model cannot do anything because they don't have data. And even if we decide to do generative AI, because the male breast cancer data is so few and far in between, and the result is not going to be good. And it's just going to contaminate our knowledge if we force fairness without doing science. So it seems that the fairness in medical field is first and above is to work with people like you, and then work with people in the field to figure out together. Yeah, from machine, we'll point out some aspect of fairness. Expert will point out some aspect of fairness, and we collect data, and then we train the model, and it cannot be solely based on AI or solely based on expert. What do you think? Yeah.
Yeah, eventually, so we still converge back to the alignment, right? Eventually, what AI should do should be really alignment with human, right? Human value and social norm. There's still two factors. So we cannot, work align with AI, right? We need to AI align with us. So along this way, even though we don't have a lot of cases, for example, like I said, male breast cancer, but we can actually more like after training, right? So in the inference stage, like reinforcement learning, you can give an award, right? More like give a positive feedback award to the system, right? Or to the negative or penalty to the system to encourage or discourage generation such kind of content. So it's because the emergent ability of generative model, you don't need a lot of cases. So many cases, many times you only need a 0 shot or 1 shot or few shots. You can actually make the generative AI can align with human values. It's not the retraining or de novo retraining. So I think that's still we are finally converged to the same issue, right? So the human feedback.
Thank you.
Well, we're at time now, so I don't know, anybody have any final comments? Well, hearing none, then thank you very much for a very enlightening presentation addressing an important problem of bias in AI. And hope that you continue this work. Everybody else, thank you for attending and for your great questions and for staying till the end. And hope to see you at the next Power Talk. And if you have any questions and you need to get in touch with Dr. Zhu, we have his contact info.
Yeah. So thank you all for having me here. I'm thrilled to have such opportunities. So if you're interested in some details or any kind of collaboration, please feel free to be in touch. Thank you again.
All right. Bye, everybody.
Bye-bye.